If you step outside on a crystal clear night and sweep the sky with only your eyes, several planets will reveal themselves as steady star-like lights. But there is one world you will almost certainly never glimpse unaided: Neptune. The smallest of the ice giants and the most remote major planet, it hides at the far rim of the Sun's domain, a frigid realm where sunlight dwindles to 1,000th of what we enjoy on Earth, and the Sun itself would appear scarcely 1/30th of its familiar size. That stark remoteness helps explain why Neptune remained for so long a place of rumour and uncertainty, a world of titanic, short-lived storms that bloom and fade, winds that roar at nearly supersonic speeds, dusky and fragile rings, and an entourage of moons whose scars and orbits whisper of violence in the deep past. Of all the planets, it is the one we still know the least about. The tale of its discovery only deepens its mystique, because Neptune is the lone planet that was not first seen and then explained. It was predicted on paper and then found where the equation said it must be. In the mid-19th century, French astronomer-mathematician Urbain Le Verrier scrutinized the motion of Uranus and noticed that its path strayed in subtle ways from what Newton's gravity would forecast. He argued that a hidden body, farther than Uranus, must be tugging at it and perturbing its orbit, and he calculated exactly where in the sky this unseen planet should lie. Acting on Le Verrier's letter, Johann Gottfried Galle turned a telescope to those coordinates in Berlin in September 1846 and, astonishingly, picked out Neptune within an hour, almost precisely at the predicted spot. Within days, astronomers also identified Triton, Neptune's largest moon, and yet those triumphs did little to dispel the planet's aura of distance and difficulty. Neptune occupies the solar system's dim threshold to interstellar space. At some points in its lengthy journey, it sits even farther from the Sun than Pluto, and beyond it stretch only dark, icy remnants. From Earth, our atmosphere and Neptune's faintness conspire against detailed views, and for most of history the planet was little more than a bluish point. The meagre sunlight at that range further complicates observation, washing out subtle structures and making long exposures mandatory. All of this meant that for generations Neptune remained an astronomical riddle, a planet found through the power of mathematics, ringed by hints and shadows, waiting for the day when our instruments would be strong enough and our spacecraft swift enough to truly make its acquaintance. For observers and storytellers alike, that origin and equation made manifest in the eyepiece became part of Neptune's identity, a reminder that the universe sometimes yields its secrets not to simple sight but to patient inference. And because the planet lives out where sunlight is weak and the sky is sparsest, everything about it conspires to make discovery difficult, from the dimness of its clouds to the sluggish pace of its seasons. Even so, the fact that we could predict its whereabouts before we could truly see it set a tone for everything that followed. Neptune would demand rigour, persistence, and long memory, and it would repay those qualities with glimpses of phenomena that are both austere and sublime. Neptune circles the Sun at roughly 30 astronomical units, about 4.5 billion kilometres, which places it 30 times farther out than Earth, and helps explain why a modern probe needs on the order of 13 years to get there under favourable conditions. That great orbital track also stretches time. A single Neptunian year spans about 165 Earth years, so since the planet's 1846 discovery, we have only just witnessed Neptune complete one full lap around the Sun. Studying such a remote world is a double challenge. It is too dim and distant for ground observatories to map in fine detail with ease, and sending a mission demands rare opportunities and careful gravitational choreography. In fact, only one spacecraft has ever paid Neptune a visit, Voyager 2, and it managed the feat by exploiting an unusual planetary alignment that occurs roughly once every 175 years, slingshotting past world after world to gather the speed needed for the solar system's frontier. After departing Uranus on January 25, 1986, snapping a parting portrait from about 1 million kilometres away, Voyager 2 cruised onward through the black at around 54,000 kilometres per hour. 3 years later, in 1989, the azure disk of Neptune swelled in its cameras, and during the close pass the spacecraft skimmed a mere 5,000 kilometres above the planet's north pole, the tightest flyby of any major world on its grand tour. In a torrent of data and images, Neptune transformed from a distant smudge into a living planet, a beaming cobalt atmosphere veined with bright, high-altitude clouds. a thunderous circulation with jet streams that ripped against the planet's rotation, and to astronomers' delight, a system of faint rings whose existence had been suspected but never confirmed. Voyager 2 also found a host of small inner moons, charted the orbits of previously known satellites, and revealed textures and features no telescope on Earth could have cleanly resolved at the time. Those discoveries were not just a catalogue of firsts, they were a revelation that the last planet was not a quiet backwater, but a restless giant swift with winds and rich with mysteries, and that our single encounter had merely sketched the outlines of a story still largely untold. That single encounter, brief as it was, became a cornerstone for decades of research, a yardstick by which later telescope images could be interpreted, and a foundation for every hypothesis about Neptune's climate, rings, and moons. Each frame, each spectrum, each radio measurement from the flyby has been pored over again and again, recalibrated as instruments improved, and compared against new Hubble, and more recently Webb observations in an effort to tell whether the planet is changing slowly with its seasons or pulsing more quickly in ways we barely understand. In the absence of a return mission, the Voyager portfolio is not just a record, it is the living reference atlas for a world we have seen only once and from one fleeting angle. Although sunlight at Neptune's distance is nearly 1,000 times weaker than on Earth, its atmosphere is surprisingly wild and dynamic, rather than the frozen stillness one might expect. The average temperature of the upper clouds hovers around 200 yet the planet's 28-degree axial tilt similar to Earth's 23 degrees, and Mars's 25 means that Neptune also experiences seasons, albeit ones that last about 40 Earth years each thanks to its slow progression around the Sun. For example, the southern hemisphere is currently in spring and receives slightly more sunlight, a small increase that nonetheless warms the atmosphere by around 10 degrees compared to surrounding latitudes, releasing methane from deeper layers into the stratosphere and making those regions appear brighter to our telescopes. Voyager 2's instruments reveal that hydrogen dominates the composition of this atmosphere at around 80%, with methane reaching nearly 20%. Since methane absorbs red light, the reflected sunlight skews toward blue, giving Neptune its intense azure hue. Yet perhaps the most astonishing discovery was the sheer violence of its winds, jet streams ripping westward retrograde relative to the planet's rotation, at speeds as high as 2,060 km per hour, nearly supersonic, marking some of the fastest sustained winds on any planet. These raging flows feed colossal tempests, including the Great Dark Spot observed by Voyager, an Earth-sized cyclonic storm, swirling counterclockwise much like Jupiter's Great Red Spot, but powered by even stronger internal gusts measured at up to 2,400 km per hour, the most extreme winds ever recorded in our solar system. A smaller vortex, the so-called Small Dark Spot, shifted from dark to light as Voyager approached, hinting that Neptune's atmospheric chemistry can change rapidly. Once Hubble became operational in the 1990s, astronomers eagerly searched for the Great Dark Spot again, expecting something like Jupiter's long-lived storm, but by 1999 it had vanished entirely, showing that Neptune's storms are transient, rising and dissipating over years instead of centuries. New dark spots have appeared since, including one in 2015 that has gradually faded, implying that giant vortices form where atmospheric bands with different speeds interact, but drift away from their energy sources and eventually break apart. Because many features are nearly invisible in most wavelengths, only ultraviolet-capable instruments like those on Hubble can track these changes over time. What puzzles scientists most is that Uranus, so similar in size and composition, exhibits far calmer weather. Overall winds on Neptune are more than twice as fast. While seasonal sunlight contributes some energy, it cannot fully explain the ferocity observed. Instead, researchers suspect that Neptune's powerful internal heat, rising from deep below the icy mantle, injects enormous energy into its atmosphere, fueling chaotic circulation in a place where the sun's warmth barely reaches. Seen this way, Neptune's weather is a story of contrasts. Sunlight too weak to dominate, but still strong enough to tip the balance here and there, internal heat rising to stir vast gyres, and a chemistry that paints the air blue while hiding the machinery that powers it. The result is an atmosphere that can reinvent itself on human timescales, raising and erasing storms as if the planet were breathing. Each apparition of a dark spot becomes a test of our models. Do vortices form only where wind bands shear, or can subtle temperature gradients or wave patterns seed them as well? With data scarce and seasons long, every observation matters, and each new image becomes a precious frame in a planetary time-lapse that may take centuries to complete. Deep beneath Neptune's violently shifting clouds lies a hidden source of power that sets it apart from its planetary twin Uranus. Neptune radiates far more heat than it receives from the Sun, implying an energetic interior that continues to churn despite the planet's extreme distance from our star. Its internal structure is thought to resemble Uranus's overall layering, yet behave very differently. A small rocky metallic core sits at the centre, cloaked by a massive mantle composed of water, ammonia and methane ices, not the familiar solid ice we know, but superheated high-pressure fluids that behave more like hot, slushy oceans under colossal compression. In the boundary where mantle meets the core, pressures soar to nearly 7 million bars, around 7 million times the atmospheric pressure at Earth's surface, and at such mind-bending extremes the methane molecules may break apart. Carbon atoms could reorganize into crystalline structures, creating an exotic environment where shimmering diamonds condense, fall like hailstones, and accumulate in a vast ocean of liquid carbon, complete with floating icebergs of solidified diamond drifting through the dark depths. Though still theoretical, laboratory experiments under extreme conditions increasingly support this bizarre possibility, suggesting that Neptune's interior may be glittering with a constant storm of precious stones. Above this mantle, the forces within the planet give rise to a bizarre magnetic field. Voyager 2 discovered that Neptune's magnetosphere, like Uranus's, is dramatically tilted relative to its spin axis, by about 47 degrees, and its centre is offset from the planet's core, making the magnetic geometry wildly asymmetrical and difficult to model. Initially, scientists assumed that Uranus's lopsided magnetic field might be explained by its extreme axial tilt of 98 degrees, but Neptune's more moderate tilt shows that something deeper is at work. Current theories suggest that the magnetic field may originate not from the core, but from turbulent conductive materials within the mantle itself, causing distortion as they swirl unevenly around the planet's centre. All planets exhibit some degree of misalignment between their magnetic and rotational axes, Earth included, but Neptune and Uranus represent the most dramatic and puzzling examples. This strange magnetic configuration supports faint aurory-charged particles spiralling along magnetic lines to create shimmering glows, but they are drastically subdued compared to the vivid auroras on Earth or Jupiter because the solar wind is far less energetic at Neptune's distance. Adding to the oddity, Neptune's auroral arcs appear mostly at mid-latitudes rather than near the poles, and are often type B, known as SAR arcs, which are practically invisible without specialized equipment. Recent observations by the James Webb Space Telescope finally captured delicate near-infrared emissions from these elusive auroras and simultaneously spotted something even more surprising. Neptune's upper atmosphere has been cooling dramatically since Voyager 2 measured it in 1989, with temperatures dropping by hundreds of degrees in just a few decades. The cause of this sharp decline remains unknown and challenges expectations, hinting that unseen processes within Neptune's interior or magnetosphere may be evolving. The more we learn about Neptune's hidden heat, distorted magnetism, and delicate auroras, the clearer it becomes that this distant world far from being simple and frozen is alive with mysterious internal forces still waiting to be understood. If Neptune's magnetism is indeed shaped in the mantle rather than at the core, then the planet's very heartbeat, its convective flows, its heat leaks, the conductivity of its exotic ices could be written into the strange tilt and offset of its field. That would mean auroras, faint as they are effectively weather vanes for deep invisible processes, flickering in response to changes far below the clouds. The recent cooling seen high in the atmosphere only sharpens the riddle. Is the upper air responding to slow seasonal geometry, to changes in solar activity filtered across 30 astronomical units, or to alterations in the way Neptune vents its inner heat? Until a new spacecraft can watch up close across many Neptunian days, the answers will remain conjecture informed by patient, painstaking observation from afar. For years before Voyager 2's arrival, astronomers only strongly suspected that Neptune possessed rings, but its enormous distance from Earth and the extreme faintness of the material made confirmation frustratingly out of reach. Against the inky backdrop of deep space, far from the reach of strong sunlight, Neptune's rings are composed of extremely dark particles, likely coated in radiation, darkened organic compounds that reflect very little light, so even powerful telescopes struggled to detect them. When Voyager 2 finally flew past in 1989, it at last revealed that Neptune does indeed have a ring system, but one unlike those seen around Jupiter, Saturn, or Uranus. Instead of bright, fully continuous rings, Neptune's system consists of 5 known bands that are incomplete and uneven, punctuated by puzzling concentrations of material. The innermost is the faint and broad Galley ring, stretching roughly 2,000 kilometers in width, yet barely visible. Beyond it lies the narrow and brighter Leverrier ring, followed by the much wider but dim Lassell ring, within which lies the slightly more defined Arago ring. Furthest out orbits the Adams ring, the thinnest at only about 35 kilometers wide, yet the most intriguing of the group. Adams hosts several bright arcs-localized clusters of dust and debris that appear as luminous patches along only certain segments of the ring. These arcs, given names such as Liberty, Equality and Fraternity, have remained remarkably stable since their discovery in the 1980s, defying theoretical expectations. Under normal physics, collisions among ring particles and gravitational forces from Neptune itself should cause material to spread out evenly over time, smoothing out any clumps. Their persistence suggests that something is actively confining them. Scientists suspect that the gravitational influence of nearby moons, possibly the small moon Galatea, acts like a shepherd, corralling material into these arcs and preventing it from dispersing. Yet even with this hypothesis, the exact mechanisms behind their stability, especially over decades, remain one of the most intriguing mysteries of Neptune's system. The ring's extreme darkness and tenuous composition make them among the most elusive in the solar system, a ghostly reminder that even massive planets can hide delicate and complex structures right at their doorstep, detectable only when technology and timing align just right. Neptune's realm is populated by 14 known moons, each named for mythological water spirits, a fitting tribute to the planet's oceanic blue appearance and ancient ties to the sea god. The 7 inner moons are considered regular satellites, moving in nearly circular, low-inclination orbits that align with Neptune's equatorial plane and often playing a guiding role in shaping and shepherding the planet's faint rings. Their motions reflect a peaceful childhood, formed from the disk of material that originally surrounded Neptune. But beyond these inner attendants lies a family of irregular moons whose eccentric and inclined orbits tell a much more chaotic story, with each one likely having originated elsewhere before Neptune's gravity captured them. The sovereign among them is Triton, Neptune's largest moon and one of the most astonishing objects anywhere in the solar system. Triton's orbit alone reveals a radical past. It circles Neptune in a retrograde direction, clockwise, while Neptune itself spins counterclockwise, a configuration that cannot be explained if the moon had formed in place. Not only that, but Triton's path is tilted a dramatic 130 degrees relative to the planet's equatorial plane, yet it is almost perfectly circular, indicating that massive gravitational interactions must have acted to reshape and stabilize its trajectory over time. Triton dominates Neptune's satellite system so completely that it contains 99.5% of all the mass orbiting the planet, dwarfing every other moon by comparison. Despite being slightly smaller than Earth's moon, Triton appears about the same apparent size when viewed from Neptune due to its closer orbit, and would hang in the sky as a large and striking object. It ranks as the 7th largest moon in the solar system, and is notably bigger than Pluto, which supports the compelling theory that Triton once roamed as a dwarf planet in the Kuiper Belt. Its frigid environment, surface ices, and density closely match what robotic explorers later found on Pluto in 2015, hinting that these two bodies were once siblings before gravitational fate separated them. Triton's capture would not have been peaceful. Scientists propose that it was once part of a binary pair, like Pluto and Charon, and that Neptune's powerful gravity disrupted the system. One partner was thrown into the darkness of space while Triton lost enough momentum to fall under Neptune's control, an event so violent it may have torn apart or radically perturbed whatever moons Neptune originally possessed. The other irregular moons, with their elongated, looping paths that can take years or even decades to complete, are likely survivors of that upheaval, their present orbits shaped by the chaos generated when Triton arrived and reshaped the gravitational architecture of Neptune's domain forever. Triton is far from a silent, frozen relic. Instead, it stands as one of the most geologically active and intriguing worlds in the entire solar system, boasting a complex surface composed mainly of nitrogen ice, mixed with water and carbon dioxide ices that blanket the landscape in pale tones, occasionally stained with subtle reddish patches. These colourful areas are likely Tholin's complex organic molecules, created when methane ices are bombarded with ultraviolet sunlight, which also appear on Pluto and reveal a shared chemical heritage arising from a common origin in the Kuiper Belt. Perhaps the most striking feature of Triton's surface is what it does not have: craters. Despite its size and long existence, impact scars are shockingly rare, which tells planetary scientists that the Moon's exterior is constantly being resurfaced by internal processes. Beneath its crust lies a rocky and metallic core, giving Triton a relatively high density of about 2 grams per cubic centimetre and making it far more massive than any other satellite of similar size, in fact outweighing all moons smaller than it combined. Heat from radioactive decay in that interior could sustain a subsurface ocean of liquid water, an environment reminiscent of Europa and Enceladus, where similar oceans may harbour habitable conditions. Voyager 2's 1989 flyby revealed countless signs of active cryovolcanism, geological processes in which water or other volatiles erupt from below like lava on Earth, but immediately freeze once exposed to the frigid surface. Smooth, unblemished plains from past liquid water flows can be seen dotted with caldera-like pits marking where cryovolcanoes have collapsed once their reservoirs drained. Some plains are bordered by raised rims, suggesting they are solidified lakes frozen in place. Long fractures and ridges snake across the landscape, likely driven by tectonic stresses as the crust flexes in response to seasonal freezing, thawing, and tidal interactions with Neptune. Yet even more dramatic evidence of activity revealed itself when Voyager 2 captured towering plumes, soaring as high as 8 kilometers into the sky. These eruptions are thought to be triggered by a solid-state greenhouse effect. Sunlight penetrates thin layers of transparent nitrogen ice, heating the darker, more absorbent material beneath until trapped gas causes the surface to rupture, sending jets of nitrogen gas and dust high into the thin air. The direction of the streaks left on Triton's plains indicates steady prevailing winds in its atmosphere, carrying particles hundreds of kilometers before depositing them into funnel-shaped dark fans. Triton's atmosphere itself, though astonishingly thin at around 14 millibars, comparable to 80 kilometers above Earth's surface, has proven more dynamic than expected. When Voyager 2 arrived, the southern hemisphere was in summer, and the atmosphere had warmed enough to thicken slightly as nitrogen ices sublimated, forming wispy clouds and supporting circulation up to at least 8 kilometers in altitude. Since that time, continued warming during Triton's long seasonal cycle may have increased atmospheric density even further, reinforcing the view that this moon, once thought to be dormant and frozen solid, is instead wrapped in a living climate of volatile ices, constantly migrating between surface and sky. The continuous cycling of nitrogen and other ices, the replenishing of organic compounds at the surface, the possible presence of a buried ocean enriched with the chemistry of life, and the ongoing resurfacing through icy eruptions make Triton a scientifically thrilling destination. Despite its harsh cold and dim sunlight, far too faint for life on the surface, the environment beneath its crust might resemble other ocean worlds, where many scientists believe life could potentially gain a foothold, leaving open the profound possibility that one of the most remote moons in the solar system could also be one of the best places to search for signs of biology in the deep, dark outskirts of the Sun's domain. What makes Triton especially compelling is how all of its systems seem to be intertwined. The timing of sunlight across seasons modulates surface temperatures. That, in turn, controls how nitrogen sublimates and refreezes. Those cycles set the stage for greenhouse-triggered outbursts that paint dark fans across the plains, and the resulting veneer of organics changes how the ice absorbs light, feeding back into the process. Add a possible ocean beneath, warmed gently by the decay of radioactive elements in the rocky interior, and you have a world where geology, climate and chemistry are locked in dialogue. For astrobiology, that dialogue is tantalizing, even if it never produces life, because it offers a natural laboratory for the kinds of prebiotic pathways that may precede biology on planets and moons far from the Sun. While Triton holds most of the attention, Neptune's other moons also tell compelling stories about cosmic collisions and the gravitational authority this distant planet exerts. Proteus, the second largest moon, is an irregularly shaped object about 400 kilometers across, surprisingly non-spherical despite its size, which indicates that it has suffered massive impacts in the past, whose immense craters prevented gravitational relaxation into a rounder form. It is even larger than Saturn's perfectly rounded moon Mimas, making Proteus's lumpy form especially striking. Closer to Neptune are several small regular moons that skim above the faint rings, some acting as shepherds that help maintain ring structure through subtle, gravitational nudges. Farther away, a population of irregular moons traces eccentric, inclined, and often retrograde orbits, marking them as likely captured objects, fragments of ancient Kuiper Belt wanderers that fell under Neptune's gravitational spell. Among these distant satellites are Psamathe and Neso, which travel on such vast, looping trajectories that a single orbit takes roughly 25 Earth years, indicating just how immense Neptune's hill sphere is, since at such great distances the Sun's gravitational influence grows and a planet must be massive, isolated and distant for its custody over moons to persist. One of the most intriguing recent discoveries came in 2013, when the Hubble Space Telescope detected a tiny moon only 35 kilometers wide later named Hippocamp. It orbits unusually close to Proteus, and scientists believe it may actually be a fragment torn from Proteus long ago, possibly during a devastating impact that created one of Proteus's enormous craters and ejected debris into orbit where some reassembled into this small and delicate satellite. Neptune's gravitational reach extends even beyond its recognized moons. A remote trans-Neptunian object known as 2020 VN40 follows a highly inclined orbit around the Sun, but completes exactly one revolution for every 10 Neptune makes, meaning it is locked into a precise 10.1 orbital resonance. This elegant gravitational choreography demonstrates that Neptune continues to sculpt and influence the outer solar system, capturing and commanding objects far beyond its immediate neighborhood. Despite all we have learned, Neptune's fierce winds, storm systems that appear and vanish, its diamond-forming interior, magnetic field tilting wildly off-center, ghostly rings bound by mysterious arcs, and moons that record ancient planetary upheavals, our knowledge remains frustratingly incomplete. Only one spacecraft has ever made the journey, and that fleeting flyby was more than 3 decades ago. Telescopes like Hubble and Webb have filled in pieces of the puzzle, but without a new mission to return to the last planet, Neptune will continue to guard many of its secrets behind a veil of darkness and distance. No approved missions are currently en route, and budget challenges have delayed many deep space proposals, although ambitious plans such as a potential Chinese mission in the 2030s offer a glimmer of hope that fresh eyes may soon inspect this ocean-coloured mystery. Until we go back, Neptune will remain a symbol of exploration, at its boldest, remote, dimly lit, punishingly cold, yet brimming with phenomena that defy simple explanation. It reminds us that the greatest discoveries are often those that lie just beyond our reach, and out among the frozen frontiers of our solar system, no planet stands further away, harder to get to, or more alluring in its unanswered questions than Neptune, the final world circling the Sun. And so, the case for returning is straightforward. Neptune is not merely the solar system's endpoint, but a key to understanding how ice giants work, how they form, how they vent heat, how they spin up winds, how they grow rings and keep them in unruly arcs, and how they capture worlds like Triton and then reshape them. A new orbiter, watching for years rather than hours, could map the seasons, follow storms from birth to death, sound the interior, trace the magnetic field through its lopsided sweep, and skim past Triton to test for the signatures of an ocean below. Until such a mission flies, our picture will remain a mosaic made from one close pass and a handful of distant looks. Enough to prove that wonders are there, but not enough to explain them.